Assalamu alaikum wa rahmatullah. Hope all are doing well at your own places. And so I found this moment to go and look for what we call as mechanical work done. So let me write here what's what I mean what will be our course of discussion in this lecture. So that's what we call as work done. When we just come across a day-to-day life situations, we take some loads by means of the manual or any kind of effort and all that, we at the same time call that it's a work. But another domain of physics, the concept of work done is totally different. Okay, how we can know by means of the physics language what the work done is all about? Let me come to know how this work done will be under the language of physics. For that, I will just consider here. Let us assume that I have the particle here, okay, on which some force is going to act along any arbitrary direction. Okay, and at the same time, if I will assume that I got the particle displacement by means of this applied force here in this direction, okay, I'll just call it, this is my displacement r vector for a given particle motion by the application of force. Okay, but the force is, it makes an angle theta relative to the particle displacement and all that. So under this intuition or under this vision, how we can go for and define the work done on a system. So we define the work done for a given system. It is notified by the letter W by convention, and we just define it as the dot product between the force and the displacement of a particle. Okay, this is how we can define the work done in physics, that the dot product of force and displacement. Okay, if I will write down this expression in a more simple form, I can write it as F or the cosine of theta, where theta is an angle between the particle displacement and the force. Okay, so this is how we define the work done under the domain of physics. So it's a kind of axiom that we can never derive it, because there are no derivation rules for axioms in the physics. Just like when we talk about the particle momentum is defined as the product of the mass and velocity of a given particle. And this is a kind of axiom in the physics, and we can never derive it. It's a kind of building block of any course and all that. Okay, just like if I want to give the analogous example of this context, when we talk about the triangle, okay, and the interior angle sum of the triangle, is always 180. This is also the kind of axiom, and we can't derive it. Okay, but where from we got the kind of this logics and all that? Behind this there is a complete the set of philosophy and all that. That's why we are getting the kind of idea how we can look for the axioms in order to develop some remarkable story and all that. So when we talk about the work done, it's a kind of axiom in physics. Okay, we have to believe it anyway. So what's basically the good thing in it? When we call something that's said to be work, that we say that work is going to be done under the domain of physics, it is this equation which will give us everything. We can say it is this equation which takes care of everything in a way that we can safely say right now under what conditions we are going to do work, under what conditions there is zero work done. Look, this theta, I told you as before, this is an angle between the particle displacement and then applied force. Okay, so this is a dot product of force and displacement, or we can also call it. Okay, so I will just focus on this thing here right now. When we call something as work is going to done, if this is my particle displacement here r, my force is going to be applied to the particle displacement, but at an angle of 90 degree to it. Okay, so my work done under this process will be 0, because the cosine of 90 is 0. Obviously my work done is 0. So it's the craziest thing that we have to believe under the physical intuition and all that. When the displacement is perpendicular to the direction of applied force, under this intuition or under this situation, we have the zero work done. We have the zero work done. We have the zero work done when angle between the force and displacement is 90 degree. Okay, we have the positive work done. We have the positive work done. Work done will be positive. Work done will be positive when particle displacement will be in the direction of applied force. I mean to say simply here, when my particle displacement and the force, they are in the same direction, means the angle between the two vectors is zero here. So my work done comes out to be positive because cosine of zero argument, it's a positive number. Okay. Number second. Number third is that when the particle displacement is in the direction opposed to the applied force, means that under the situation when an angle is 180, so under this situation we will get a negative of work done. And this is a very very basic side. It's not a big deal here to understand, because we can confirm everything when work done will be positive, negative, or more logically zero. It will be confirmed on the basis of this cosine of argument. Okay, so more about this work done. Basically, it is a scalar quantity. It is a scalar quantity. That when we talk about the scalars are generally some simple numbers associated with the units. They have nothing to do with the direction. But under some situations, we have some physics quantities, or we can say the physical quantities. They possess direction as well, but at the same time, we don't call them, they are vectors. Just like the current has a magnitude as well as direction, but at the same time we can't say it's a vector because it does not follow the laws of vectors. And there's a good piece of physics behind this, why it does not follow the laws of vectors. Generally, when we talk about the current, just it's not a proper moment to discuss that thing here, but I will just use some little intuition that when we say that some physical parameter, it has both direction as well as the magnitude, but at the same time we don't call it's a vector. The finest example of this context is in current. Current is not a vector, although it is composed of both magnitude as well as direction. I told you it's not a proper moment to discuss about this thing because this story is totally different here. We call something as vector, that any vector, it should follow some vector laws. This is a necessary and a sufficient condition for something to call it as vector. Number one. Number two is that basically when we talk about work done is simply what we call as a scalar parameter. But in my language, I define the scalar in a way that scalar is something that's invariant under rotation. If we just rotate something, it seems to be invariant and we just call it's scalar. Okay? We can never hide the scalar under rotation, or we can never hide the vector under rotation. Okay? So we got some kind of conclusion how we can define the work done on a given system. It is simply defined as the dot product of the applied force and the particle displacement. Okay, or in more simplest terms, we can say that it's F or the cosine of argument between the two parameters and all that. This is what's the definition of work done lies under the domain of physics and all that. I told you as before, basically this work done, it is simply a scalar parameter, that it is simply a number associated with units. It has no direction. Okay. So more about this work done. When we talk about the units of this work done, its units are joules. Okay. The SI unit of work done is joule, and 1 joule is basically equal to 1 Newton meter. 1 Newton meter. 1 Newton meter. Okay. So this was about some little intuition about this kind of guy in the physics, that what we call as mechanical work done. Okay. So if I will look for this expression, there are some another possible ways to write down this expression. Just have a look here how we can write down the same expression in another form. Just like if I will just remind my picture here, when I create the definition for the work done here, when we talk about my particle displacement is here, and the point of application of force is here. This is my force that's active on a system, and the system, it poses some displacement. Okay, this is my angle theta here. If I will just resolve my force here into its components, its one component will be here and another component will be here. The component of a force, applied force along the displacement, we will call it its F cos of theta, and the component which is perpendicular to the particle motion, we call its F sine of theta. If I will just look to this problem, basically, F sine theta, it will not contribute to my work done. Means that perpendicular component of the force, it will not contribute to the work done. It is basically the parallel component of force that contributes my work done. Okay, so perpendicular force will never do any kind of work done. Okay, so if I would write that my work done by means of the perpendicular forces, okay, so perpendicular forces will never contribute anything to the work done. There will be zero contribution to the work done from the perpendicular force. This is an important kind of conclusion I am getting here. More logically, if I will use this concept in case of the particle motion, if my particle moves at the same time, if the perpendicular force acts on that particle motion, what will happen there? Very important. Basically the perpendicular force component, it will bend the particle trajectory. Perpendicular force component will bend the particle trajectory. You might have heard it from the theory of, the curved, or I can say more logically the circular motion. If I will just draw my curve here, okay, every curvature has a center, okay, let us assume that this is my radius of this curvature. But for me, if I will just impose here some physical event, for example, if I want to know my particle velocity at some particular point on this trajectory, I am eager to draw the tangent, because tangent has a kind of property. It basically meets the curve at some particular point. This is indeed the definition of tangent. So it will give us everything that we logically wants to know, how particle motion will be, in which direction the particle motion will be along the curve at some particular point. The better way to represent our particle motion, we are going to draw the tangent. Okay, not only this, when we talk about what will be the direction between what will be the the angle between the radius of curvature and the particle motion, it's by some geometrical argument, we know that it's perpendicular. Okay, it's 90 degree. It's the angle between the particle velocity during its curved motion and what we call as the radius of curvature, that comes out to be 90. What's my point of interest here? More logically, my point of interest here is basically to say that the perpendicular force component, it bends the particle trajectory. The bending of particle trajectory, what it means, and basically it alters the direction of velocity. If at this particular point my particle velocity will be in this direction, but the perpendicular force act on a particle along this direction, it is basically responsible for bending the particle trajectory and all that. What it does to the system, basically it alters the direction of velocity, but it does not speed or slow down the particle velocity. It does not speed up or slow down the particle velocity, although it alters the direction of the particle velocity and all that, and it makes the contribution to the bending over the particle trajectory and all that. If the local curvature of the particle motion, it is being confirmed from this guy, and sometimes we call it's known as the centripetal force. Centripetal force means it's towards the center of this particle motion when it follows the kind of curve. Basically, this force is responsible for bending this curve. It is nothing but here the perpendicular force. I remind here the kind of consequence of this perpendicular force. It bends the particle trajectory in a way, it alters over the particle velocity, but it does not make any appreciable effect on what we call as indeed it makes zero effect. It has zero effect on the particle speed. It can't either speed it up or slow it down. But there is a parallel component of force which is responsible for either it can speed up the particle or slow it down. Depends upon whether we are going to do the positive or the negative work done. It will be confirmed whether the force acts on the particle, or I mean to say more logically here, the parallel component will be along the particle motion or will be in the direction against the particle motion. It will be confirmed at some given point of interest. But my point of interest here is simply that The parallel component will be either in the direction or opposite to the direction of particle motion. Under that situation, we will be have with some kind of work done. Okay, but preferentially when we talk about this perpendicular component of the force, it has no role in case of the work done. Okay. So this was some key idea, some little key intuition regarding what we call as the work done, how we can define the work done under the domain of physics and all that. So I mean, I will do some, let me go and look for the simple problem of this context, that if under some situation I need to calculate the work done on a system, how I can calculate it. Let me just mention here the problem that's based on the work done. Simple definition that we got so far. The axiom of this force that we got so far, axiom of this course that we got for so far, it's my fellow here. So I want to do some simple problem of this context here, like for me, if there exists a kind of block here, okay, but this block it rests on some horizontal rough surface, okay. If there is a block, okay, and if this is my block here, okay, the block, it is in a context, it is in a contact with what we call as the horizontal surface, but this surface is basically rough in nature, and there is a greater, I mean, probability or expectation of having what we call as the coefficient of friction, that's known as mu. Okay, I mean to say, so far here the block I have, it is going to rest on some horizontal rough surface having some coefficient of friction. In addition, if the mass of block is given as m, okay. Now furthermore, if we will apply some force to this block at an angle theta relative to the horizontal direction, okay, this is my horizontal axis here, it makes an angle of theta to it, this is my direction of applied force, okay. And this block, it basically moves and it covers a distance of x. It covers a distance of x. I need to calculate how much will be the work done by means of this force, okay? Or we can say the number of forces which are going to involve here. What will be the work done by means of all these forces here? Let me come to know this thing. The force which is going to apply to this block under this vein, what will be the contribution of work done from this force? So I can write my expression here once more. It is F or cosine of theta. Look, if I can write it as F x cos of theta. X is given, cos of theta is given. I need to calculate here only what we call as this force guy. If I will be successful in order to calculate this force guy here, so my whole job is done, means that by means of which I can get my value of work done, okay. So how I can calculate it? Have a look here. I will use here the kind of simplest assumption here. When I apply force to this block, what will happen to it? It will not suddenly move. Means that when my block is barely to move, under that situation, if the number of forces which are going to act on the system, it will represent what we call as the equilibrium position of the force, situation of the force. Okay, very important kind of assumptional model I am going to use here. If I will apply the force on this block, the moment I am going to apply the force on this block, and suddenly this block does not move. Means that when my block is barely to move, when my block is about to move, under the situation or the condition that happens to occur here, just I want to tell it once more, very important condition I am just talking about here. The moment I will apply the force on it, this block, it will not suddenly move. Means that the number of forces which are going to act on it, it will give me the proper balanced condition by means of forces and all that. So let me analyze here what are the number of forces which are going to act on this block. Number first force will be weight of this block because of its mass, okay? And this is the first force that I can look for here. And number second force there will be the kind of reactional force imparted by the surface to the block. It will be in this direction because it is as a consequence of the Newton's third law. This will be my normal force. Okay, that forces they should must act in pairs and all that. So not only this, if I will just resolve this force into its components, it should have one component here, that will be F cos theta. It will have one component here, that will be F sin theta. Okay. So the number of forces which are going to act on this, I got here so far, but there is one more force because of the roughness of this surface and character. Obviously, we can feel here the kind of what we can say the frictional force. If I will just represent by frictional force by this way, so this is what I can, the subscription of F I use here, it's meant for the frictional force. Okay, by this way I am getting the kind of success in order to analyze what are the number of forces which are going to act on this block. Okay, if I will use the kind of assumption here, as I told you before, the moment I am going to apply the force on it, it will not suddenly move. It will not suddenly move, but it's given in a problem that we have the kind of displacement at some later time. But we can first of all look for the equilibrium of forces here for a given moment. Okay, so the number one force here, because this one, so how much, what kind of means that the forces along the vertically upward downward, they should balance in pairs, means this force plus this force F sin theta, it should be equal to yes mg. This is my first condition here, that I can number this as first. So number second condition is basically my F cos theta is equal to yes. Okay. Or I can look for the problem through one more way. Basically, if my block, it moves with a uniform velocity, okay, or if you can understand this way, my block, it just moves with a uniform velocity, that again represents what we call as an equilibrium condition by means of the forces. But we can calculate the work done by means of this force by using this condition here. Condition will be same, but I am just proposing the same thing by using the different kind of statement. If my block, it moves with a uniform velocity here, okay, on this rough surface, and it achieves the kind of displacement x, so by this way, how much work done will be by means of this force, applied force F here. For that, I am just using the same equation here, same kind of mechanism here, but it will give us the kind of good understanding by this way. Okay, so this is my n plus F sin theta, it will be mg. F cos theta will be the frictional force here. So if I want to know, if I will just define my frictional force we define it as, yes, by definition, it's mu times n. Mu time is the normal reaction. If I will just put the value of normal reaction here, yes, it will be yes, mu, it will be mg minus F sin theta. Okay, and my frictional force is equal to the F cos theta, it will be equal to F cos theta. So I will get here F cos theta, yes, it will be mu mg minus F sin theta. Okay, after doing the further maths, I will get here my F, it will be cos theta plus mu sin theta, it will be equal to mu mg. Okay, or I can write my F, it will be simply equal to mu mg over cos theta plus mu sin theta. By this way, I got the value of this F. I can switch this value here, so I will get the work done by means of this force here. So what will be the form of that work done? Yes, my work done in this process, it will be simply yes, mu mg cos of theta x, yes, over cos of theta plus mu sin theta. And this is my work done by means of the force F here. So by this way, my problem ends. It's a kind of appreciated expression recording the work done. Okay, So by this way the problem ends here. Thank you.